Welcome and hello. This is a video tutorial in HEC HMS, and in this lesson, I'm going to be discussing meteorological models, specifically the different temperature methods. All right, let's go ahead and get started. What I have on the screen here is my HMS. I have a basin right here with two sub-basins. They're there. So let me bring those up into screen. And then I also have started with a meteorological model that I've created. And then in the basins tab here, I've said to yes, include sub-basins from basin one. So these two are linked together. The main meteorological model tab here in my Met1 includes temperature as a dropdown, and this refers to the temperature method. So our options here are gridded temperature, interpolated temperature, Metsim temperature, and specified thermograph. So in this lesson, we're going to be discussing these four different methods. Air temperature is a major factor in HMS because it affects the evapotranspiration, shortwave radiation, longwave radiation, and snowmelt. Let's get started with our first method, which is the gridded temperature option. And as you see, we have a gridded temperature icon here that appeared in the Watershed Explorer. So I'll go ahead and select that. And now in the components editor, we have the different parameters that we need to define. The only required parameter is this grid name. And what it's referring to is an air temperature, precipitation, data, and grid name required. That's not right. It's air temperature. So not all the labels are correct. So I'm going to go ahead and create a grid here. I'm going to go up to components and then grid data manager right here. And then for the data type, I first need to select temperature grid set. So do that and then click new and then give that grid set a name. Just type it in and paste it in like I did. And then you can use a description as well. If you have a bunch of grid sets, it may be good to use a description to help identify which one is which. But for just this lesson, I'm just going to go ahead with a name, click create, and then there is my grid set representing air temperature for basin one. So I'm going to close my grid data manager. And now I have this grid data directory that popped up in my Watershed Explorer. So if I expand that and then expand the temperature grid sets, I now have the grid set that I created. From this grid set, I can actually define the data itself by selecting a data source, either a single DSS record or multiple DSS records. So whichever I select there, I would need to provide a DSS file by navigating to the DSS file with my data sets, or the file path is what it's called, and then defining the path right here. If we go back to the gridded temperature icon, then we can select that temperature grid basin. The most common use of the gridded temperature method is to utilize radar-based temperature estimates or when data is derived externally from HMS on a grid. Down below the grid that we select, there's an option to perform a time shift. Now, different methods are either none, normalized start, or user specified. If we select none here for the time shift, then no time shift occurs. The other methods are like the normalized start method. This method adjusts the time of the first grid in the grid set to the start time of the simulation. And then the last option here is user specified. This method is used to correct for temperature grids stored with a time zone offset. So what we need to do is select the time shift in number of hours here, either up or down, to account for that time zone discrepancy. The user's manual says that if the temperature grid set is set to Coordinated Universal Time, UTC, and the local time zone of your model is in the Western Hemisphere, then you want to use a positive time shift. But if your local time zone is in the Eastern Hemisphere, then you're going to want to use a negative time shift. So let's go back up to our meteorological model. The next air temperature method for a meteorological model is interpolated temperature. This method uses interpolation from point data recorded at different weather stations of known locations to create a temperature grid across the watershed or subbasins. So I'll go ahead and select that, and then I'll click on my interpolated temperature icon here in the Watershed Explorer. And now what I see is different interpolation methods. So before I can do this, I need to actually define some time series data sets for air temperature records in the area. And then here is my basin map again. So the distance in interpolation methods is really important. Each subbasin and everywhere on the map you can see has a northing and easting or an XY coordinate system or latitude, longitude, whatever you're working with. If I click on a subbasin, for instance, I have a latitude, degree minute second, a longitude, and degree minute second. Same is true with subbasin 2. And I'm actually going to change that to decimal degree because I just prefer that. So tools, program settings, and then latitude, longitude, I'm going to change that to decimal degree and then click OK. All right, there we go. So just a single field. Let's go ahead and create a few gauges with latitude, longitude values for that air temperature by going to components. This is going to be time series data manager. Now we want to select temperature gauges. Okay, and then new. I'm going to give it a name, temperature gauge 1. While I'm here, let's go with temperature gauge 2. And for a good measure, let's do temperature gauge 3. Okay, that's enough. In the Watershed Explorer, we have temperature gauge data, temperature gauges, and now gauges 1, 2, and 3 that we just created. This gauge data can be defined here in the components editor. We have a number of options. For instance, data source can be manual or a DSS record. The units, Fahrenheit or Celsius, the time interval. This is a time series data set, so the interval is the duration between time steps in the data. Here's an elevation, reference height, and then the all-important latitude, longitude, which we would have to put for the location of that air temperature gauge. All right, so once we go ahead and get this primary metadata assigned for our time series data set, let's go ahead and click on the plus symbol to expand all the time windows. The default time window here is the first day of the year 2000. So go ahead and change that for the start date time and end date and time for the duration of your simulation or more. It needs to at least include the duration of the simulation. And then once that's done, you can type in or paste in the actual temperature values for that gauge. So once that's taken care of for all your gauges, we have air temperature gauges on our map as well as subbasins and other points of interest. We can go back to our interpolated temperature method in the meteorological model and select our interpolation method. So our options here are inverse distance squared, nearest neighbor, and bilinear. Inverse distance, if we select this option, basically the weight or the importance of a temperature gauge is proportional to its distance to the point of interest based on a 1 over distance weight method. So that basically means the closer the gauge is to the point of interest, the more weight that the value of that air temperature at that gauge has on interpolating the temperature at that point of interest. The inverse distance squared method is similar, but instead of 1 over distance, it's going to be 1 over distance squared. So that just makes the distance between the temperature gauge and the point of interest that much more important. For inverse distance and inverse distance squared, there's an equation here that basically shows that this z value would be the air temperature in this case at location xy. And you could also say at time period t. And it's a factor of the different air temperature Z at gauge I, which has a distance D from the gauge to the point of interest sub I for all gauges I, for gauges I 1 through N. And then there's also an exponent factor here, P. It's kind of hard to see, but if the P is 1, then anything raised to the 1 is itself. So that's disregarded. That would be the inverse distance method. If P is 2, then it's distance squared. That would be the inverse distance squared interpolation method. And then next up is nearest neighbor. This is the simplest one, I believe. It's basically just takes the same value as the nearest temperature gauge. So it discounts and disregards any temperature gauge that's not the closest one. Lastly, we have bilinear. This method involves HMS creating a triangulated irregular network using the air temperature gauges locations, where each gauge location is a corner of one or more triangles. The temperature gauge at each point of interest involves identifying which triangle it's located in, and then computing its air temperature based on the air temperature of the 3 gauge locations defining that triangle. I also have an equation for the bilinear method here, or triangulated interpolation it's called. Basically, the air temperature at a point of interest, F sub P, would be a linear function of the 3 different temperatures, F sub A, B, and C, which are the air temperatures at the vertex points that define the triangle. These lambda terms are weights, lambda 1, 2, and 3, and that's based on the area of the point of interest and the other two locations of gauge locations. Also, within the interpolated air temperature method, we have a few other things to consider. These are optional, but an adjustment method can be made, either none or lapse. Lapse refers to a lapse rate where we need to define how the air temperature changes in degrees Fahrenheit for every 1,000 feet, because oftentimes higher land surface elevations can have lower air temperatures. So just using the terrain data that's associated with the basin model, then that lapse rate or that temperature correction can be made. So just go ahead and type in a number there for that. At the bottom here, we have this table where we list out the gauges and the radius of influence. So what this does is it allows the modeler in HMS to completely disregard any gauges that are beyond a certain distance. So what I would do is just say gauge 1, for instance, has no influence after 100 miles of distance. For most of these interpolation methods, as the distance grows, the influence or the weight drops anyway. But this table here at the bottom allows the user to explicitly remove any consideration of that gauge's air temperature value from the interpolation calculation. Let's go back to our meteorological model here and temperature. Our next air temperature method is Metsim temperature. So if I select that and then I click on the Metsim temperature icon, I've got a few options here. This method takes the daily maximum and minimum air temperature values at different gauge locations and interpolates sub-daily air temperatures using a spline polynomial. The temperature disaggregation model is bond. That's our only option, so that's what we use. So we need to define the daily min and max temperatures, and these are going to be grids. So it's not the same thing as the basin map that we have already defined because we want the daily min and the daily max. Once again, I'm going to go up to Components menu and then Grid Data Manager, and then I'm going to select Temperature Grid Set. Of course, we have one for Basin 1 already. That's not what I want. I'm going to go ahead and create a daily min for Basin 1. And then once again, I'll create a daily max for Basin 1. Okay, so those can be defined just in the Watershed Explorer and the components data, just like we did for Basin 1. And then I should be able to select them here. So here's my min, and then here is my max. Also worth mentioning that this method, the Metsim temperature method, requires that the subbasins use a discretization method. So what that looks like is if I click on the subbasin, down in the components editor, I have a discretization method right here. It's currently set to none, but it needs to be set to any of these non-none options, structured, unstructured, or file specified. And that's true for all the subbasins in all the basins that are associated with this meteorological model. More details on discretization are found in lesson 15 on this playlist, and it's titled Subbasins Discretization. Let's go back to our Metsim temperature icon parameters here. In the components editor, I now have to specify the time of max daily temperature in minutes. And then if I hover over, it just says between 0 and 1440 minutes. So that's how many minutes are in a day. So I believe it starts at midnight and just moves forward. So if I just typed in something like 960, that would be 4 p.m., just 16 times 60. And then below that, we have time shift. Our options are none, normalized start, and user specified. These are the same time shift options described in a previous temperature method. All right, back to our meteorological model. The last temperature method here to select is specified thermograph. This air temperature method allows the user to directly tell HMS what air temperature values to use for each subbasin. That way there's no interpolation and there's no equations involved. So what we would do is select our specified thermograph icon. And for each subbasin, we quite simply just select the time series data set that we want to use. Right now I'm seeing data sets for gauges 1, 2, and 3, and that may be what we want to use in certain situations, but more likely than not, we would have a separate time series data set that we want to define just for that subbasin. So I'm going to go up to Components, Time Series Data Manager, Temperature Gauges, New, and then I'm going to just say explicitly this is for subbasin 1, and then New. Let's make one more for subbasin 2, and there we go. So those are right here, subbasins 1 and 2. And then to actually make that assignment, I would go ahead and say 1 and 2. This method would be used if temperature data was calculated outside of HMS and then imported in. The last thing we need to specify is the time-lapse method. So right now I just have a column for gauge. Let me save that. And then if I switch it to fixed, I now have a column for lapse rate. Now, it doesn't give me any units or description, but from the previous method, I'm pretty sure this refers to the temperature correction based on the elevation of the ground surface. So using the terrain data, the air temperature would most likely decrease as the elevation increases based on the units of degrees Fahrenheit and 1,000 feet of elevation. But yeah, I'm not seeing the units here, so I'm not 100% sure that's the case. All right, well, that was it for our discussion on different temperature methods for our meteorological models within HEC HMS.